Okay, this is right about where we left off, right? So the abstraction, and the separation of the what and the how. What is a stack, but how do we implement a stack are two different questions. You've understood the concept of a stack your whole life without ever thinking about how it was implemented in Java before, and that's entirely fine, right? And again, like I was saying with Python, you all use the lists in Python, but you didn't know how it was implemented. But that's entirely fine. You just used it and you were able to do what you needed to do with it. Great. And you did that all independent of the how. You didn't need to know how it does what it does. You know what you could do with it, but how was it implemented? It didn't matter. In this class, we are obviously going to be implementing the how. We're going to define a stack, we're going to use stacks, but we're going to implement a stack. So obviously we're implementing it, but we're going to implement it in such a way where we keep these ideas as separate as possible. In fact, Java gives us some nice built-in tools for doing that in a very nice way. Okay, layering. If our systems are large, we like to start to have layers of abstraction. And this is more along the lines of what I was talking about, like picking up a marker versus contracting muscles and tendons and neural signals and ion pumps. Like there's layers there, right? That's the example, like how do you cook pasta? Well, boil some salted water and then add pasta, right? That's how you make pasta. But we could go into more detail. Anyways. Yeah, if I want to make pasta for dinner, I don't care about ion pumps in your neurons, okay? I don't care. There's a lot of layers of abstraction between cooking pasta and how your neurons are firing. So back to data structure. A data structure is an actual implementation of an abstract data type, ADT, abstract data type. Now, like a lot of things in programming, I and everyone else will be a little sloppy with our terminology. I'm going to do my best to be very precise when I say ADT collection versus like a data structure. A data structure is more of a concrete implementation of something where the abstract data type is like the idea. But it's pretty common to interchange these words all the time. I'm going to do it. Fortunately, if you're thinking, how am I going to keep track of the context of what we're talking about will probably make it pretty darn clear. But I'm going to do my best to keep it as straight and clean as possible, but anyways. So the contact list example, the what would be, we'll keep track of friend objects, add, remove friend objects, get a friend object, and so on. But the how would be like, well, we used an array to store that information. And we did a linear search to find and check if a friend was in that collection. That's the how. The what and the how are separate. Like I was saying, a large focus of this class is going to be on both, but we like to keep them separate. And we often call this separation layer, we call it like the interface. How I interface with something and how something's interface instructs it how to do what it's doing. The interface is like the layer that we often like to point to. Yeah, okay, it's not uncommon for people to use data structure as a catch-all term to mean ADT in specific implementations. That's normal, but again, yeah. So any questions? So this really is like the intro topic. We did all this review for the first few weeks. Now we're ready to start 162. Cool. Make sure this is going. Good stuff. All right, the stack. The stack abstract data type, ADT. Stacks are linear collections of elements. And all the adding and all of the removing of the elements happens at one end of the stack that we call the top of the stack. This isn't new. This is something that you're familiar with. Now, we use two words to mean add and remove in the context of a stack. If I say add to a stack, I mean pushing. If I see pushing, that means adding to the stack. Pushing, you push something on top of the stack. And when you remove something, you pop it off the top of the stack. Those are the words we use. They just mean add, remove. But when you push something to the top of the stack, such that it becomes the new top. If you pop something from the top of the stack, well, it was the top, now the thing below it is the new top. But push, pop, they're the fancy words we use for add and remove. You can also find other names for a stack, especially if you go like back some time. Sometimes they're called pushdowns, but that's more of an older word to mean stack. Stack is like a stack. And given this, a stack is what we call a LIFO, L-I-F-O, data structure. The last in, first out. The last thing I add to the stack, if I remove something from the stack, the last thing I added would be the first thing out. Okay? This is as opposed to like a queue, yeah, which is going to be like the last thing in, or like the first thing in would be the first thing out. I call it FIFO. So consider the following example of a stack. A stack of plates, like you see at a buffet, web page history, kind of you can think of as a stack. Right, like think of like if I go to a new website, and then a new website, and a new website, and a new website, the current website I'm on is like at the top of the stack. If I hit back, I just go down, right? And same with like undo, right? If you're typing in your word processor like Word, and you're making all these changes, then you hit undo, well, they go in like reverse order, right? In the order in which they would have been like added to a stack. So a stack, this data structure actually has like uses there. And it's kind of neat, right? Like you're writing all this stuff in Word, you undo, 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 you do more stuff, you undo, undo, undo. Like it's this ever growing and shrinking stack. Same with like your web page, like back, 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 you know, you can keep going. But like you can think of it as like branching, right? Like even though a stack is a linear data structure, you know, it can kind of branch. Like if I'm from like one website to another website to another website to another website to another website, and then I decide to like go back, like okay, I'll go back a page, click another link, go back a page, click another link, click another link. It's kind of like I'm like backtracking almost, but then I can continue from like some point in the past to, you know, it's kind of neat.
So it's a tree?
Kinda. It's still a stack, but like it's funny how you can kind of see that relationship, right? Like the state of the stack at any given time is a linear data structure. But if you kind of think of like its stack existence over time, it kind of has that like branching feature, which is kind of neat, but not overly important right now. A call stack, which when you hit run on your programs, you may have seen something like this in Java already. When you hit run in your program and your program crashes, raise your hand if when working on assignment you ever had an exception and your program crashed. Of course you did, right? If you didn't, you're weird or you're lying. So one thing that you might see is you see like a stack trace. You ever notice something like that? Yeah. Well, a stack trace, that's a stack, but more on that another day. So here's a stack. Here's my stack of pancakes, right? This pancake's not on it yet. This is the top of the stack, the bottom of the stack. If I add the new pancake, it's like, well, that's the new top, right? The bottom remains unchanged, but the top changed. And then if I go and I remove something, well, there's now butter on the pancakes. And the top, well, if I remove that top one, now the new top is the pancake that was below it. A stack. Someone really wanted that pancake. And look, if you're going to eat any pancake in that stack, that's the one you want to eat, right?
No, the way to do it is multiple at once. You gotta dig your fork down all the way to the bottom.
All right, and then just go for it. Okay, stack. With all of these data structures we're going to build, we're going to create the same general operations. We want a way to add something to the collection. We want a way to remove something from the collection. And often we want a way to like look at something on the collection but leave it there. Then we want to do like, okay, check if it's empty and tell me how many things are currently in the collection, right? These are the common things we're going to implement for the collections we're going to make. A way to add, a way to remove, a way to like observe but leave unchanged. And then check if it's empty and see how many things are left on the stack. When we make a queue, we're going to do the same thing. When we make a tree, we're going to try to do like the same thing. A bag, same thing. But the way in which, first of all, as for how the stack is defined, there are some strict rules about how we add. If it was a sorted bag, like a sorted list, and I wanted to add a number, well, there's going to be very strict rules on how we add to it. So the way we add and its behavior will depend on, well, what's the data structure we're going to make. Yeah, so the way this is done is going to differ based on the type of collection. And in addition to these things, you know, a lot of times it's quite nice and helpful to do a toString and an equals. That's just like for any object we make. We want a toString, we want an equals, it's nice. And if we make an equals, we should have a hash code, so yeah. So we're going to include those as well. But these are the ones that we're like, okay, these are like the collection-y things that we care about. Any questions so far? It's just ideas. All right, so stack. So to add something to a stack, we call this push. And when we add an element to this collection, the element is always added to the top. Always. If you say, well, what if I want to add it to not the top? Then it's not a stack. But I want it to be a stack. Well, then you add it to the top. But I don't want to add it to the, then it's not a stack. A stack is defined such that whenever you add something to it, it goes to the top. If you don't want it to be like that, then use a list. Use something else. It's not a stack. Pop, we remove an element from the collection, and the removed element will be from the top. Again, if you're like, but what if I want to remove like the thing below the top? Then you don't want a stack. This is a stack. You add to the top, you remove from the top. Now, you'll notice that like push, when you add something to the top of the stack, you're changing the state of the stack. This is a very stateful object. When you add something to it, well, it's different now. In the same way that our contacts, our country catalogs were stateful, but it's very stateful. Remove is very stateful. And like, well, what will happen here? So I remove an element from the top of the stack. The element after the removed element will now be the new top, assuming it exists. It's possible that it was the last thing on the stack, and then if I pop it, well, now it's an empty stack, whatever. And something that's neat about the remove here, the add, or the push, no, the pop, my God. The pop is when I remove an element, it's returned by the collection. Now, if you go, like I made a bit of a stink in previous lectures about how like add and remove return booleans to conform with the collections. But stacks are a little different, and same with queues, that when you remove something, it returns the thing you're removing. It returns a reference to the thing that you're removing. So it's a little bit different. Peek is like pop, except it returns a reference to the thing at the top of the stack, but it leaves it on top of the stack. So you peek at it, but you leave the state unchanged. So this operation doesn't affect the state of the stack. Yeah?
So when you remove stuff, you're removing it from the top, but would it be possible to peek somewhere that's not the top?
Nope. We're not supposed to, at least. Now, you can go find definitions of stacks where like, okay, that's possible. Our definition, we're going to keep it as simple and pure as we can, where it's all the actions happening at the top. Now, if you're paying attention and you're like, well, if you do a toString, presumably you're going to like print out the whole contents of the stack, and you could thereby like observe in some way what's in the stack. Yeah, fine. But we don't really have this like programmatic way to like specify an index and return a reference to that thing, right? What you could do is use like 2 stacks. If you really wanted to be able to peek at some other area in the stack, which I maintain, then don't use a stack. But if you're like, I found the exception to the rule where it really has to be a stack, but I really need to know where something else is. What you could do is like you have 2 stacks where you go like, okay, take the top, put it there, take the top, put it there, look at this one, and then take the top from here and put it there, right? You kind of see what I mean? Yeah. If I had a stack, okay, top, bottom, and an empty stack, and I popped everything off of this stack and pushed it onto this stack, what's at the bottom of this stack?
The top thing in the old one.
The top thing from this one. What's at the top of this stack? The bottom. We flipped it. You reversed it. Stacks are kind of neat like that. Yeah. I saw another hand somewhere.
I was just going to ask, are you recording? Or?
I think so. I hope so. Yeah. Good catch. It's always good to ask. I've been known to forget. I know you want to watch me later, I know. All right, so peek. Yeah. It's against the definition of a stack to access anything from anywhere else other than the top of the stack. That's the rule. Why? Because we are defining a stack. And if you say, but I really want to, that's against the definition, right? Because we are defining a stack and then we're going to implement the stack. Okay? Okay? Any thoughts, concerns, comments, or anything so far? Okie dokie. So, the stack abstract data type. The above describes the what. What can I do with the stack? But you'll notice, like I've been saying, at no point have I described the how. Where's the data that we're storing in the stack going to exist? What container are we going to put it in? Container is a word to just mean like where are we going to shove that data to keep track of it. We don't say anything about like, well, how do we actually add anything to the stack? How do I do the toString for a stack? How do I add something to a stack? That all depends on the implementation. Those are implementation details. Obviously, they're going to be important because we're going to implement it, but these are separate issues, separate questions. And this also has nothing to do with Java. None of what I said here has a single thing to do with Java. It's just an idea. I could implement this in real life by making an actual stack. I can implement it in Python. I can implement it in Java or C++ or whatever language I want. It doesn't matter. These are just ideas. So with only the what, it's still possible to solve problems with a stack. You don't need to know anything about how a stack does what it does. All you need to know is what a stack does. So imagine I have this little maze here, okay? Maybe it's like a little robot starts at the green one and wants to get to the red one, right? And look, obviously we know, there we go, right? You can move like one cell at a time or whatever, right? Great. But if I want to write a program to solve this maze, to solve it, how do I do that? Well, with a stack, it's remarkably simple. Take a moment, look at this, and I want to give yourself a minute. Take a minute, think about what I'm showing you here and what I just said about a stack. How could you use a stack to solve this maze? You can talk amongst yourselves if it helps.
Are you just asking us to think about it, or do you want like an actual answer?
I just think about it. I mean, if you come up with like, I figured it out, good. But it doesn't have to happen. If you look at it and you're like, I'm stumped, whatever, that's fine. So here's the idea. We're going to use what we call a depth-first search. Now, a depth-first search is a form of AI. It's a very simple form of AI. But it is a form of AI. It's like a heuristic. Like if you follow this set of rules, you will find a solution to this maze. It's going to work. So it's a very simple one. The high-level idea is this. Pick a path that's not visited yet. Okay? Travel down that path until you find the end of the maze, or you get to a dead end. If you're at the end of the maze, you're done. If it's a dead end, backtrack until another path opens up. And repeat this process. The backtracking is handled by the stack. Like the top will be like the last cell, the last spot we visited. And so if I'm at a dead end, I can backtrack by popping that off the top of the stack, which would take me back to the previous cell. So let's say, look, it's a program. We need a systematic way to solve this maze. So we need a way to say, okay, whenever we get to a new cell, we're always going to check up, right, down, left, like a clock. Okay? So we're going to first check up, then check right, then check down, then check this, right? So let's say we start here. Start at the green cell. Okay? Is up a valid location? No. Is this? Yes. Perfect. So we will push that onto the stack. Is up a valid one? Yes. Okay, push it onto the stack. Is up valid? No. Is right valid? No. Is down valid? Yeah, but we were already there, so forget it. Is that? No. We're at a dead end. Pop. Now we already checked up, so we checked there. Is that valid? No. Is that? Yeah. Go there. Check up? We came from there. Check right? Oh, we can go there. Check up? No. Check right? Yeah. Check up? No. Check right? Yeah. Check up? Okay. Check up? Yep. Check up? No. Check right? No. Check down? We came from there. Check left? Oh, there we go. Up, right, down that. Dead end. Pop, 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 pop. We now have another valid path. Down, down, check right, we're done. That's the idea. If I went too fast, there's a GIF that will go fast for you too. So there we go. So this is the idea. This is some visualization of what's going on. The dark blue is like the current cell. Gray is where we visited, and orange is like an exhausted path already. Yeah?
Do you call it a GIF to start arguments with everyone or stop arguments?
That's exactly why.
Very good.
Because it makes everyone mad.
Cool.
Is it a GIF? Is it a GIF? No, it's a GIF. So I don't even think about it anymore. I just say it. I've been doing it for so
That
long.
makes it so much funnier.
Anyways.
I didn't even recognize what you said. It's just like GIF. I'm like,
Yeah.
That's great.
Is it random?
No, I systematically say always check up, then right, then down, then left. You could make it random, but usually you want it to be a little bit more systematic than that, where you've got some set of rules that you're going to go. Yeah.
I wonder if it was random, what the probability of just getting to the right path.
Well, it'll happen. I mean, we could calculate it if you really want, but it depends on how you implement the randomness. Now, you could imagine the behavior would change a little bit if I changed the order, right? If I said check right first, and then down, and then left, right, or then up, down, right, left, whatever. If we change the order, as long as we did it systematically always the same way, it would have predictable behavior, but its behavior would change depending on the order in which I checked. At the end of the day, the valid path is the gray path, I guess. Hooray! And then we start over. This will always work. It can get a little bit more complicated if we allow loops in the maze. But if we keep track of places we've already visited, then we're fine. Now, what's neat about this maze is it's guaranteed, or this algorithm, it's guaranteed to find a path, but it's not guaranteed to find the shortest path. It'll find a path. And you can really cheese, if you know, and this is actually kind of an interesting observation that's worth exploring, is if you know something about how the algorithm works, I can create an adversarial instance. That's a a well-defined term, an adversarial instance, an example maze layout that is designed to be like mean to the algorithm. So I can do that and make it like its worst case scenario, for example. Yeah.
But you can start making it worse by implementing bubble sorting.
But what am I sorting?
Oh, I just mean more along the lines of, hey, these are all of your options that you can go in. Randomly shuffle it until you manage to reach a combination that gets you to the end. Then you can have a real worst case scenario.
That's terrible.
Yeah, that's terrible, yeah. All right, so okay, here's like the pseudocode of the algorithm. Now, remember that the algorithm in Java, sure, a Java code for this algorithm is an implementation of the algorithm, but the algorithm is the more general idea. Remember how like the general idea of a linear search is start at the beginning of your collection, look at each thing, and as soon as you find it, you're done. If you don't, keep going until you do, or if you get to the end and you don't find it, you're done. Like that's a description of an algorithm, the steps, like the high-level idea, but it's separate from the implementation. So here is like the pseudocode. Pseudocode meaning like it kind of looks like code, but this ain't code, right? Somewhere in between. So add the start of the maze to the stack. Well, the stack is not empty. Get the top of the stack with a peek to look at the current cell. If the top is the end, we're done. If an unvisited neighbor of the current cell exists, push the neighbor onto the stack. Otherwise, if no admissible neighbor exists, pop from the stack. And that's it. If the loop ever exits because of an empty stack, there's no solution. That's it. Meaning, like, we've got a maze where there's no way to solve it. It's the only way. Is if you go all the way and you eventually pop off the start of the maze, then, yeah. So that's the algorithm. That's it. Any questions about this idea here, how we're using a stack? Push, 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 pop, 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 push, 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 push. We're done. This follows that algorithm. The only thing here is I say if any unvisited neighbor of the current cell exists, push it on the stack, push the neighbor onto the stack. Otherwise, that's like the else. The only thing missing there is the fact that like I'm systematically checking in the order of like up, right, down, left. But that's the algorithm right there. Any questions about this? Yeah.
I don't know if this is the appropriate question right now, but how would it like save like where it went? I guess if if I.
Oh, we would need some form of bookkeeping.
Yeah.
That would be not on the stack. Like somehow we know like, okay, look, I already visited that. And maybe we could do something like a set or something. There's some way to keep track of it. So bookkeeping would be needed, yeah.
Okay.
Yeah. All right. So yeah, whatever. Try to see where the push, pop, and peek operations are happening. We kind of did that already. Again, we described the algorithm without needing to know any of the how. We don't need to know how the stack works. But we could still use it to solve the problem. So what we're going to do now is define the interface. We are going to define the what. What we're going to do, listen carefully, because this is a whole new concept that we have not covered in computer science yet, but it's important. We're going to create a whole new thing called an interface that defines what a stack can do. But it does not define how, but it defines what. And it's a well-defined what. So, there are a lot of ways we could implement a stack, but the what is going to be the same for all of them. When you open up the hood, I don't care what kind of vehicle or engine you got under there. It's still like a car. I can get me from A to B. I don't care how you implement the stack, as long as it's a stack. If it does what a stack is supposed to do, it's a stack. How does it do it? I don't care. I just care that it conforms to my definition of what a stack is. And we are defining this in the interface. So we can create a whole thing, a whole new idea. We write the code to define an interface. It defines what the operations of our object are going to be. The interface only defines the what. It does not talk about the how. Your comments to describe like the spirit of what each thing is supposed to be, but we don't define the how. If someone wants to go and implement the how of a stack, they must implement the interface. Okay? If let's say I say I'm writing down what a stack is. And then you want to show up and say, I'm going to implement the stack. And I say, in order to guarantee that you have to implement everything in here. Okay, would you agree? If I define a stack and say, stack, this is a stack. Okay, and you're going to come along and you're going to be like, I'm going to make the super stack. It's an implementation of a stack, and it's the best one there ever is. And I say, okay, great, that's great. So if you're making a stack, you implement everything in here. Okay? And if you say, well, I didn't really, then it's not a stack. You have to. And in fact, Java gives us a way to say, you want to implement a stack? Great. You need to promise me, guarantee, that you implement what a stack is. And if you do, then you're a stack. If you don't, I won't run. More on this, you'll see what I mean with an example. An interface, at the end of the day, an interface is just a list of methods. But they're not even methods. They're abstract methods, which is a fancy way to say it's just like the declaration line of a method with no actual code in it. For example, it would say int some method, whatever, semicolon. That's it. That's all it has. There's no code in that method. It's just the definition of a method. We're going to see the example for a stack. It should click pretty quickly. And it would also perhaps include some static final constants if necessary for whatever you're making. So here is the stack interface. I would write this into Java. I have not included the java.comments for the sake of space here. I'll load it up in a moment. But what we see is public interface stack. You see this weird magic less than t greater than? More on that very soon. But you'll know, okay, it's not public class, it's public interface. This ain't a class, it's an interface. Okay? And in it, we have push returns a Boolean. Pop returns something of t. Peek returns something of t. Boolean is empty, int size. So this is return type size. You'll notice that I don't say public here. If it's in the interface, it would have to be public, but we just kind of ignore it here, by the way. Because the interface is this is everything anyone could use for a stack. Meaning, if you implement it, it must be accessible, meaning it must be public. It just has to be. So, yeah. Return type, name of the method, any arguments it takes. Semicolon, no contents to the actual methods here, though. Just the names of the methods. If we go here, let's... No. Yeah, download the insecure file. No, what? Yeah, this one. There we go. You would see something like this. Now, there's a lot of Java docs in here, but these are just describing what a stack is. So, right, a stack is a linear data structure that has all the actions happen from one blah, 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 right? Push pushes an element to the stack. The push adds the element to the stack such that it becomes the new top of the stack. Param element, the item to be pushed, added to the stack. Return true if the element was pushed, false otherwise. All right? It's describing the behavior with Java docs. It includes the signature of our method, but there's no actual method there. All right? This is all it is. This is, if you're like, but where's the code? There is none, because that's not what this is. This is not the how. This is the what. You want to make a stack? This is what it's got to do. What do you want to do? Push, pop, peek, is empty, size. Whoop. Any questions about this interface idea? We're going to hit that weird T in a moment. Now, what on earth is that T? Well, that brings us to generics. I'm going to explain what generics are with an example. All right, so we haven't talked about this yet, and it wasn't needed in Python because of Python. But yeah, like I said, this is probably best explained with an example. Let's say I want to implement a stack with integers on it. Now you'll notice, first of all, this is not int, this is integer. More on that in a moment. But I want a stack of integers. Okay? All right, so looking at this, if I have a stack of integers, what should the type of the thing being pushed be? Integer, right? And then if I'm popping, what should the return type be? Integer, right? Great. So I would need to go and define a stack interface for, okay, Boolean push integer element. And then someone comes along and they say, well, now I want to make a string one. Okay, let's go to find a whole new interface for a string, where, okay, we've got Boolean push string element, friend, or a string pop. And then we want a friend stack, right? All right, well, now we need a new stack so we can have friends that are the type of things we go onto it. Obviously, this is ridiculous, right? We would need a whole new definition of what a stack is for every possible type. What generics are variable types.
So it's like a way to have a subclass for a stack almost. It's like you have like your class is stack, but then it has the subclass of integer.
Well, it's like we have a class stack, but what is the type of the things in the stack? That's what we're doing here. Now, so what this means is if you want a stack of integers, when you create an instance, you'd be like, I want a stack of integers. And as long as the types match up, we're good to go. If you make it integer, T is integer. Integer element, integer pop, integer peek, everything's fine. Strings, great, string, string, string. As long as everything matches up, it's fine. But when we create an instance, we specify what the type is. I'll show you an example of that shortly. This is something that makes, like, it won't click until it comes full circle, but the motivation is it's a way to have variable types. So yeah, if I wanted 3 different types, I'd need to have 3 different interfaces for the stack. And obviously, why would I stop at 3? There's a bajillion different types out there, right? I can keep inventing new types. I'm going to need a new interface for every type? No, we use generics. So T is a stand-in for the specific type that can be specified later when the stack is created. It can be thought of as like a variable for a type. Although jumping ahead a little bit, consider the following example. Like array stack. What's array stack? Don't worry about that right now. We're going to talk about that very shortly. The way I say is the type is stack, but the things on it, the generic type, is integer. So I'm making a stack of integers. That's what's going on there. All right? All right. In fact, over here, you could even put like a question mark. Or no, not even a question mark. You can use what they call the diamond operator. Basically, you leave this blank, and Java will be like, well, it's going to be an integer. By the way. Yeah, I've got a note there for that. When creating an instance of the stack, the type is specified within the less than and greater than, or triangle brackets, whatever. In the above example, with the use of generics, 3 different stacks are created, each with a different type of object as its contents, but we only needed the one interface because When I call it here, the t was integer. When I call it for this one, the t was string and friend, and so on. So I have 3 different stacks, each with a different type as its contents, of its type of things on the stack. Okay? That's what we're doing here. And then, like I said, if I specified it here with the reference variable, I could actually leave this blank, and it will know. It's smart enough to know in this particular case. Any questions about what I just showed you? This, I maintain that like all I'm doing is, you got to remember like Java was made by software engineers for software engineers that knew what software engineers wanted to be able to do. And unfortunately, we are new programmers trying to learn how to do all this type of stuff, right? So some of the stuff, like, you kind of have to see the big picture before it all makes sense. So I'm just trying to give you a sense of where we're headed to get a sense of where the big picture is, but acknowledging, like, full well, we got to know, like, we don't really know what the big picture is yet. So we do what we can. So don't be too worried if that wasn't quite clear yet. Once you start doing it, you put it in action, I think it'll help quite a bit. Now, the funny thing here is, if I want a stack of ints, you can't do it. You can't. But you could have a stack of integers. Integers are just ints. But they're the object version of primitive types. You can't have generics use primitive types. You can't. But every primitive types are like your double, your int, your bool, your character, right? Those are your char. Those are your primitive types. If you really want to put primitive types on the stack, you use the object version of those types. They work and behave all like the same way at the end of the day. Now, why do we need, first of all, why do we have primitive types? They're simple, the computers love them. They're great, okay? But when you enforce that everything is an object, if everything's an object, everything inherits from the object class, and everything in the object class, guaranteed, has a toString, whether you implement it or not. Guaranteed to have an equals. So there are some guarantees that if this is an object, we can do anything an object can do. Right? If it's a primitive type, I can't guarantee that. So we just use the object version. This is not a concept you have to have a full knowledge of at this stage. If at this stage, all you remember is, if I want to have a stack of ints, I can't. They need to be integers. They need to be the object version of the primitive type. If that's your takeaway, that's fine. But there is a method to the madness there. Yeah?
So the object version always just like the primitive types only?
Not always. Because like, I don't have an exhaustive list in my head, but like int and integer, and the object versions always start with an uppercase, because that's the convention that we follow in Java, right? So if I wrote like versus, these are both doubles, but the bottom one is an object version of a double. Int versus integer. There's bool versus boolean. Char and char is char? Yeah, character, yeah. So there we go, yeah. So that's the object version. Pardon? There is no primitive type string. Strings, there's no primitive type string. It's the object. Strings are always objects. That's why every string we've ever had in Java starts with an uppercase S. By the way, it's an object. You're like, well, what if I want the primitive type? There ain't one. A string is already like an aggregate of characters, right? So it's already a little bit more fancy. Okay, generics, yada, yada. There has to be a better way. There is. Yeah, cool. Yeah, it's not possible to use primitive types, int, double, boolean. In generics, instead use the object version, etc. Again, that's because if Java knows that this thing is an object, whatever I get, it's a generic, right? I've got some generic object T. Whatever it is, I know because it's an object, and because I inherit from the object class, we've got a dot equals implemented. Whether I overrode that equals or not for the specific object is a different story, but the point is it exists. Same with the toString, it exists. So as long as I get an object version of something, I can guarantee it's an object, so I can do anything I can do with an object with the objects. Any questions about the general idea of the interface and the stack, ADT, or generics or anything at this stage? All right, so now we just described the what. Well, okay, let's now describe the how for a stack. And we're going to make an array stack. Now, there's a convention in Java where your interface, your definition of what something is just its name. So I want to make a stack, so we define the stack interface. But in implementation, the name of the class that's implementing an interface will follow the convention with like a more specific thing. Like we'll have an array stack. It's going to be a stack made with an array. That's the convention, okay? We're going to make a linked stack soon, made with a link structure, which we're going to learn about soon. All right. Now we know what a stack can do. It's time to start discussing how. So there are a few implementation issues or questions we need to consider. How are we going to store the data? And, you know, depending on how we store the data, that then leads to another question of like, well, how do we keep track of the top of the stack? We're going to implement a stack with an array. Arrays are great for storing contiguous data. When you can use an array, use an array. They're fantastic, right? So here's an array of size 10 storing reference to 6 elements, 0 through 5, right? Assuming I'm using an array to keep track of like the contents of a stack, how should I like configure all of this? Like where's the top of the stack? How would I update the top of the stack? If I add something new, where should I put it? You know, these are some questions we need to consider. And I think there's no sense going any deeper based on the time of today's lecture, but that's where we're at. Any questions before we wrap up for the day? Okie dokie. All right, we'll end here for now. Otherwise, yeah, have a wonderful rest of your day. Good luck and have fun shoveling snow.
But it's supposed to be a snowstorm or something?
Oh, yeah.